There's a hole in my bucket, and ant-men are leaving the hole, making the bucket lighter as time goes on. All right, so part A wants us to draw 3 graphs on the same grid for each of the 3 forces on this bucket. So it asked us to do it for the first 15 seconds. So I'll label the time axis. It's going to go up to 15. There's going to be some important times in the middle that I'm going to identify, but we'll add those in a bit later. In terms of forces, let's do some analysis of the forces here. Starting with the free body diagram. So I'll start at t equals 0. At the very beginning of this thing, this bucket's on a table at rest. And then it's actually 2 kilograms at this time because it's 1 kilogram itself, and there's 1 kilogram worth of ant-men inside of it. And rope's going to start pulling up on it with 15 newtons. That's the tension. And that's going to stay constant, actually. So that graph's actually going to be the easiest one. It's just going to be a horizontal line at 15 newtons. But let's calculate some gravity here. So gravity, m times g. So it's 2 kilograms at this point in time, times 9.8, giving us 19.6 newtons. So that's a bit longer. I'm going to draw a bit longer arrow compared to 15 newtons. And the bucket's at rest on the table, and you may think the person's going to pull it, so it's going to move upwards, but it is not going to move upwards right now because 15 newtons is not enough to overcome the gravity. But I do need the forces to balance out. It's not going to fall through the table either, so the table is going to provide a normal force that needs to get this balanced out. So this normal force, what's going to balance out that 19.6? It's going to be 4.6 newtons. So that 15 plus 19.14, 15 plus 4.6 is 19.6. Okay, so I'm going to start by labeling the vertical axis as force in newtons. I'll use up as my positive direction here. I'm going to start with the tension force because that's going to be the easiest one. It says the tension stays constant at 15. So I'm going to make a mark at 15. And just have a horizontal line, and this is going to be my tension. All right. The other one that is, now the other two are going to be more challenging, the gravity and the normal force. So the gravity is not going to be constant because the ant-men are going to be jumping out of it. So it's going to lose mass at a rate of 100 grams a second. It's going to lose mass at a rate of 100 grams a second because the ant-men are leaving through the hole. So when will we run out of ant-men? When will all the ant-men be gone? That's going to be an important time in this scenario. So 1 kilogram is 1,000 grams. And we are losing ant-men at 100 grams per second. So that, just do the math there, that's going to be 10 seconds. So therefore, no more ant-men at 10 seconds. So that's going to be an important point in my graph I'm going to plot. So that's about 2/3 of the way to 15. So the force of gravity is going to start at negative 19.6. Here, I'll just make these increments of 5, 10, 15, 20. So negative 19.6 is just slightly before it hits negative 20. And then at 10 seconds, when we're out of Ant-Man, now it's just the weight of the bucket, the empty bucket. So the empty bucket is 1 kilogram. And 1 kilogram has a force of gravity of 1 times 9.8, so 9.8 newtons. So at this 10-second mark, we're actually going to be at negative 9.8 newtons, so slightly before the negative 10 mark. Oh, it does not go at 0, it goes at 10 seconds. And then after this, so from 10 to 15 seconds, it's just going to stay the same mass from there on. So the force of gravity is going to be negative 9.8 newtons for the final 5 seconds. So in between there, the Ant-Men are leaving at a uniform rate. The Ant-Men are leaving the bucket at a uniform rate. So that's going to cause this to be a straight line. Okay, so the blue is gravity. And now normal force. So the normal force starts at 4.6. I'll mark that down first. We had calculated that in our free body diagram at time equals 0, so slightly less than the 5 mark. And what is going on with the normal force? Well, the normal force is actually getting smaller. See if we can understand why. And it's because the gravity is getting smaller. So the normal force is what's keeping this bucket on the table. It's preventing gravity from pulling it down. But the gravity is getting weaker. The gravity is getting weaker as the Ant-Men leave it. So over time, we need less and less normal force to keep this bucket on the table. And at some point, actually, the bucket's going to leave the table. The bucket's going to leave the table because at some point, the 15 newtons is going to be bigger than the force of gravity. So what we need to figure out is when will the force of gravity be 15 newtons? When will the force of gravity be 15 newtons? So that the tension can overcome it and there's no longer a need for the normal force. Well, that's going to happen when mg equals 15. And that's going to happen when the mass is equal to 15 divided by 9.8, which is 1.53 kilograms. When does this happen? When is the mass? So the mass started at 2 kilograms. At what time has it reduced to 1.53 kilograms? Well, remember the Ant-Men are leaving at 100 grams a second. So what's the difference between 2 kilograms and 1.53 kilograms? That's 470 gram difference. So after 470 grams of Ant-Men have left, which since they leave at a rate of about 100 grams a second, that would be 4.7 seconds. So this is going to be an important point in my graph here. Well, I'll label 5, and 4.7 is slightly before 5. At that point, there will no longer be a normal force, because the tension is going to be bigger than the gravity at that point. So the normal force, we need less and less and less of it as the Ant-Man leave to keep the bucket on the table. And at this 4.7 seconds, now we no longer need any normal force. It's going to be 0 for the rest of the time. So those are the forces. And there is a lot going on there. That's why this is a challenge question here. The acceleration as a function of time in part B. Like I used all my space. So I might not actually talk about B and C here, but they would also be challenge questions. You can keep thinking about that if you wish. I would not really put it on a test or anything like that. But if you can figure it out, then that's quite significant understanding. You have not only of all the concepts, but also of graphing, getting your graphing skills there. But I will talk a little bit about part D. Why are we using Ant-Man leaving the bucket instead of like water coming out of the bucket, which may seem more natural. But the problem with water is that if water is trying to force its way through a hole, maybe at the bottom of the bucket, it will actually not leave at a uniform rate. It will leave quicker at the beginning when there's more water because there's more pressure pushing down on it, so it'll leave the hole faster. But once the pressure has reduced, then it's actually going to drip slowly towards the end. So the water does not leave the bucket at a uniform rate. That's why we needed something like the Ant-Men, which are capable of leaving at a uniform rate because they're Marvel and they can do anything in Marvel. All right.